Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is state-of-the-art diagnostics technologies for proactive condition assessment. My name is Michael Fleischer, and I'm the digital marketing specialist from Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Robert Probst, Product Manager. Also, to assist with the question and answer session, we will have joining us Marshall Bird, Sales Manager, and Henning Ochin, Product Manager. All right, let's go ahead and get started. Thank you so much for joining us today, Robert.
Hello, everybody. So welcome to the webinar on state-of-the-art cable diagnostics and condition assessment. So I've prepared an agenda that is a little different to other webinars that we have done on the topic. And so first of all, regarding the topic, state of the art, I want to discuss what is this, state of the art? What are people talking about? What is the industry doing right now, okay? Then a little, in between part, why are we even doing this? And where did it all emerge from, okay? So what are the technologies? Why are these technologies there? And, a little bit of a historical component to all of this. Then we will be talking about Vlf testing, about partial discharge testing, and about 10 delta measurement, which is the last and the shortest chapter. And you will see why. And then at the very end, as a question, so where are we going from here? Okay, so if this is the state of the art, what is going on in the future? Or what are, for instance, typical best practices in the field? What are people doing? This kind of thing. Okay. So first of all, state of the art. So what is the state of the art? So first of all, as a central topic of this presentation, people have to recognize and acknowledge that there's different types of cables and different types of faults. And, in terms of the life cycle of the cable, you always have this aspect of commissioning testing. So you have new cable. That's very important. That's its own world kind of thing, okay? So for new cable, you have to do acceptance testing or more broader commissioning testing. Then you have another world, which is the world of the serviced aged cables. So these cables have been in service for 5, 10, 20, 30, 40, or even longer years, and they're definitely not new anymore. And then you have this, modern philosophy view, which is the so-called state of the art, that you use these technologies that you are seeing here for the different types of cables, new cables and serviced age cables, that is considered to be the complete picture. So if you do Vlf testing, partial discharge analysis, and 10 delta measurement, you are getting the full picture. You're getting everything that is actually measurable in today's world of field testing. And at the very end, you will see why this picture on the left is, at least a little bit under fire, okay? So now, why are we doing this? There is a historical component to all of this cable testing. And one aspect is, how has the cable infrastructure changed over time? So first of all, we started 140 years ago, 150 years ago, if you want to push it, with underground cabling, okay? And those underground cables, they were what's considered paper cables, paper insulated cables. there were many different varieties. There was gutta percha and all of these different things, but essentially they were laminated insulation cables, so layers of paper and then some fluid. And the fluid actually is the actual insulation medium. All of these cables were belted cables, and once they became three-phase, and there was a limit. You could not exceed 20 kV because otherwise the cable would fail. In 1913, a guy named Martin Höchstätter, a German professor for high voltage engineering, came up with a solution for that, and he put a perforated metal foil around each individual phase of the three-phase belted cable. And that fixed the issue. It turned these belted cables into what's called radial field cables. And then you could exceed the voltage of 20 kV. And that was pretty much the start of this, development of voltage, higher voltage, ultra high voltage. So the same thing that you had with overhead lines also happened in the cable world. And in the high voltage segment, 1927, Luigi Emanueli at Pirelli, which is today Prysmian, introduced the oil pressured cable, the low pressured cable, and that is the pipe type cable, if you will, and that is the technology that was for many decades the dominating technology in the HV transmission type cable world. And then in the 1970s, a big shift happened. So people moved away from paper cables to solid dielectric cables. And to put it politely, there was a big learning curve associated with this, because the first few generations of PE, of polyethylene cables, were terrible for various reasons. The curing process was an issue initially, and other things. So when the third generation of PE cable came into the world, was was introduced to the marketplace, it fixed a central issue of these PE cables, and that was the water treeing. So anything that is put into the ground since the late 80s, early 90s is not just regular PE anymore. It's tree retardant PE, or in general, if you want to describe these cables, those are copolymer cables. And the interesting thing here is that all the testing methods, they were tailored to the oil cables, to the paper cables. And the question was, is that even applicable to solid dielectric cables, to extruded cables? And the answer later found by the scientists was no, it's not. And that was one of the aspects why certain testing technologies emerged. And then, of course, there's the other aspect, the aspect of, money. So every utility company has a limited budget, and the reliability of the grid, of the network, of the system is very important, because it's also very often one of the key performance indicators how well a utility company is doing in general. So, there was a replacement for the DC testing, which became Vlf testing. And that is pretty much can be described as preventive maintenance or preventive testing. So you'll find some defects, and then the next iteration, the next evolution was to go from preventive to predictive maintenance testing. And this is all done because you want to reduce the outage minutes. And very interesting statistics. For example, the SAIDI index of, let's say, Germany is 11 something minutes a year. The mean SAIDI of the United States, with with some utilities doing a little bit better and some utilities doing a little bit worse, there are definitely differences. That SAIDI index is on average somewhere around 120 to 150 minutes. And that is already corrected for major events, storms and everything. And that has to a certain extent to do with the type of infrastructure, with the amount of overhead versus underground and all of these things. And to actually reduce the outage minutes to justify all this testing is pretty much then ending up on the table of the asset manager. He is the guy sitting on, the chest with all the gold in it, and he has to say, well, my budget is limited, so where do I get the biggest bang for the buck? So he has to make a decision how to allocate those limited resources. So, and spending it on cables, judging the cables by age, installation date, has not proven to be very good. And throwing dice is also not like a solution. So they want a scientific, a technical approach, right? And all of this preventive and predictive testing, that is pretty much the base for the asset management to then make a decision and to do their risk assessment. And make no mistake, some people, especially the people who work for utility companies, they think they work for a technical company, but essentially, if you look at this, you're working for a bank, okay? You try to maximize your return of investment. And then in terms of where did the technologies come from, so you saw we have something that is called Vlf testing, we have something that is called partial discharge testing, and we have something called 10 delta testing. Well, it all started in 1983 technically, but 1986 was the patent of the Vlf technology. So that was kind of like the beginning of everything. Immediately after that, the technology went into the market, it hit the industry, and it became the standard tool for maintenance testing, replacing DC testing. And the first Vlf standard was the VDE, which is the German national standard, which was issued in 1997 to include Vlf testing now and not allowing DC testing on polymer cables anymore. Then in the mid-90s, the resonance testing emerged, which is because of equipment size, cost, and all of these details reserved for high voltage transmission cables. It has not taken on in the medium voltage world. It's simply not, not cost effective. And also in the mid-90s, a second VLF waveform was, pioneered or, constructed, which was sinusoidal test sets. Also in the 90s, the questions about, okay, what is my main insulation doing in the cable came up. So there was various different methods. And as you can see, only the 10 delta prevailed because later on IRC and RVM are not mentioned anymore. Technically, from a very deep technical point of view, IRC and RVM are superior to 10 delta overall because you get more out of the test. But you have to take it with a grain of salt. It's also more involved. And for that reason, it has not caught on in the market. It pretty much vanished. And the 10 delta is the leftover, winning by not being eliminated. And almost simultaneously in the early 2000s, the partial discharge field testing, came into the market. And I want to emphasize field testing because the partial discharge testing as a factory acceptance test or a quality test was already established at this point at the cable manufacturers with stationary equipment. So it was laboratory grade testing, which then transposed into the field. And since then, especially since the 2010s, everybody is now thinking more in a broader way and thinking condition assessment, combining multiple things and to get a good picture of your cable installation. And now another thing we talked about, you have different technologies, you have new cables, you have serviced age cables, and very important which also affects the technologies, you have different types of faults. Generally speaking, you have so-called local issues and global issues. The local issues are anything that is very limited in, in its spatial dimension and very located to certain things in and on the cable, namely the accessories. So local defects are directly related to the accessories, and the global issues are, with respect to the homogeneously aged main insulation of the cable. And then for the local weak spots, you also have two classes. You have a very straightforward type of fault that is solely dependent on the maximum field intensity. So just apply a high enough voltage, the fault will ignite and burn, or buzz and deteriorate, and that's it. And then there is a type of fault that is mainly in the accessories, that is very sensitive to the gradient of the voltage, and that will be very important later, so keep that in mind. You have local issues and global issues, okay, that affects the technology you can use. So the local issues are typically addressed with the PD test, and the global issues can be addressed with the 10 delta. And then within the local issues, you have pretty much voids and things like that, which just ignite by application of a high enough voltage, peak field intensity. But then you have the much more complicated and much more common problems, which are these problems in the accessories in the so-called layered interfaces. So keep that in mind. There's one class that is straightforward, and then the other class is very sensitive to the gradient of the voltage. And now to VLF testing. So first of all, what is VLF testing? Well, it's very straightforward. It is nothing but a high-pot test. It replaced the DC high-pot test. It's an overvoltage test that pretty much tells you I have good insulation or I have bad insulation, and the judgment is the cable holds or the cable fails during the test. It is done preferably at 0.1 hertz. There's, internationally speaking, IEC. The IEC world has a fixed frequency. IEEE allows for frequency reduction. VLF testing is non-destructive. That means it doesn't introduce additional weaknesses into the cable. There is two different waveforms. You have to apply it for an extended period of time, typically, specifically on serviced age cables, because you want to treat the water trees appropriately. We will get to this in a second. And there's various standards, mainly the VDE, Senelec, IEC world, and then the IEC, the IEEE, excuse me. And the result is a pass-fail. So it is a high pot, yes and no. It holds or it fails. That's it. Nothing more to learn. And then, as I always say, you always win when you do VLF testing, because first of all, you're doing this in a planned outage. So whatever happens, nothing happens to your index numbers, okay? So your SAIFI, SAIDI, CAIDI, CAIFI, no impact there. If the cable passes, congratulations. International studies show now in 97 out of 100 cases, your circuit will be quiet for the next 3 years from aging, from aging induced faults. If the cable fails, I also say congratulations, because now you have a faulted cable. You caught something on your own terms and not while the cable was in operation. Very big difference. Ask your asset manager. He will explain to you the difference. And hopefully you have your cable fault locating equipment on standby, because then you could go out and connect the search generator, the TDR and everything to immediately fault locate, find the fault and repair it. Or you have a bypass, backup cable, backup circuit ready just to do the switching in time. and then you come back later and treat the cable later, repair the cable later. So failing a cable during a VLF test is a good result. It's not a bad result. And then in terms of test standards, those are the main standards internationally. And I want to point out the parameters. Typically in the IEC world, it's 3 times operating voltage. Operating voltage is always abbreviated with U0, which is a line to ground, phase to ground voltage in RMS. And so in case of a cable, this is really the voltage that is applied between center conductor and shield. Testing time is typically 1 hour and the frequency is fixed to 0.1 hertz. And then I want to point out a difference here, which is significant in practical testing. IEEE is diverting from the commonly established IEC test practice. As you can see, the values are given in the as a function of the waveform, which is not the case in IEC. I will get to this in a second. Frequency reduction is allowed as a loophole. Testing time is a little different, and specifically the test values are very different from the IEC test values. And how this shows in the field, you can see here. So if we have our time base and we use the typical cosine rectangular waveform, then 3 times operating voltage at 0.1 hertz looks like this. Now IEC says the test voltage has to be in RMS, which has scientific reasons. We will get to this in a second. So doing the same test with the sinusoidal test set looks like this. That ensures and guarantees and is proven to produce equivalent test results between the wave shapes. So IEC is independent of the wave shapes because it's defined as RMS, and you can use a sinusoidal test set. You will get the same reliability numbers as with a cosine rectangular. And now IEEE, unfortunately, decided to define this. The cosine stays the same, but the sinusoidal gets a special treatment. So the standard is biased towards sinusoidal to the sinusoidal wave shape. And the problem here is what you're trying to do during the test is directly related to the RMS and not to the peak. Yes, ignition of a weak spot is a function of the peak voltage, but that's not the issue here. The growth of the trees, as you will see in a second, is a function of the energy, and the energy is related to the RMS. So it can be argued that if you do a test according to IEEE values, you can ask the question, is that really a comparable and as good of a test as if an IEC test? And unfortunately, there was no numbers investigated on this. We have the 2 international studies that prove the IEC approach, and that's pretty much it. So we have to say we know this is okay, and this is probably not that okay. Now, just a little historic background. This company here that you see, you saw it in the other slide. It's actually funny. It's a naval yard, and in this naval yard, they pioneered the VLF technology. And since this company is related to us through like weird family ties, I always say if you have a very good year as a utility company with a good budget, we also sell you hydrogen-powered submarines if you want to. Half price if you buy 2. So on the VLF testing, how it all started. Well, I told you already, it started in '86. Well, technically the test set was under development since '83. And in '86, the patent was issued. The lead engineer was Ekkehard Lehfeld at HDW Electronic in Kiel, HDW Electronic in Kiel. And he came up with this idea, I have to build a test set with a certain waveform that has to be designed to have a field test equipment that is replacing the DC test is an AC hypod in contrast, and achieves all these nice things: small, compact, lightweight, powerful, and duplicating as much from the AC testing as possible. And the waveform he pretty much came up with looks like this. You have a plateau-like phase, and then you have a polarity reversal that is as fast as the power frequency, and that will become very important later on for the PD testing. So the waveform has several nice features. Even the smallest test sets have a huge testing capacity. So a very common European testing practice is you parallel all three phases together to save testing time. Instead of three times 1 hour, you only test 1 hour all three phases. Or, you know, if you do it at reduced testing time, it's even faster than that. The slope of the waveform makes it applicable to PD testing, as was confirmed later on in several practical studies in 2006, 2008. And you can do a very nice monitored withstand with this. That means you do a VLF withstand test and you trend the PD while you're doing this. Here's just the patent. So for the interested, you know, for the expert in the amongst the viewers. Now, why is this water treeing effect such a thing? Well, before the tree retardant stuff was put into the ground, first and second generation PE cables suffered a lot from this. And also EPR cables have treeing as well, approximately as much as water tree resistant cables. And so water tree is pretty much this pocket of water. There's various different models to explain this. With, you know, nano voids that are filled with water and then expand and all of these things. And the water tree grows over time and it distorts the field. And at one point, the field intensity is compressed in such a small volume that the dielectric strength of the solid dielectric is exceeded and an electrical tree is ignited. And that electrical tree is a gas discharge in solid. So a gas discharge in a solid is only deteriorating and it grows much faster than the water tree. So it will fail the cable very shortly after it was conceived for the first time. And now, just to discuss this for a very brief moment, VLF is non-destructive, and what that means is, you know, if you don't have faults in the cable, it won't fail the cable. The cable will pass. There are other hypod tests that have the sole intention of failing the cable. This is not one of these tests. It's not a step test. So very early on, the Europeans found, well, this is non-destructive, and also then there was a NITREC study on that when IEEE made their standard, or their guide, I should say, and the same thing was found. If you apply the prescribed values, no other weak spots are introduced into the cable. You only find what is already weak. And now, very importantly, you know, I told you about the RMS values, I told you about the testing time, and this is pretty much the essence of that. Why is that important? Because very early on, it was found by researchers that if you do the test at elevated voltage, for instance, 3 times U0, you have a significant acceleration of the electrical tree growth, which is important because otherwise it would be silly. If you only grow the trees as fast as AC power frequency, then you could, you know, forget about the test because you just let it sit at operating voltage, right? So you have to have a time advantage. So you have a much faster growth rate under VLF stress at higher voltages than compared to 60 Hertz operating voltage. So that makes the test viable. Then they pretty much found that 0.1 Hertz is okay, 0.01 Hertz or anything below 0.1 Hertz is not. And also very interestingly, the you know, right now the SIGRE working group that is extending these testing specifications or these testing rules into the high voltage cable world. They also, as far as I know, it's not really finalized yet, but 0.1 is the threshold. Slower is a problem because then you get into other issues. So they recognize 0.1, but nothing slower. And the problem here is you don't do the same test anymore when you reduce the frequency. And then some people are like, okay, then I extend the test time, or they argue you could extend the test time. And I challenge this. I pretty much asked them, okay, so show me a single guy that is doing that in the field. A lot of people, they simply don't do it, because if you really go as low as 0.1 hertz, to compensate with the testing time means turning a 1-hour test into a 10-hour test. It's not going to happen. People will still do the normal time, so to speak, and they are not doing the same stress in the cable. And also what also came out of this research, even if you would extend the test time, it's still not the same dielectric stress in the insulation. And then, very important, the main takeaway message here is the non-equivalence of RMS and peak, because this research and the researcher who did this, he pretty much told us and gave us a letter on this. Yes, this was all done in RMS values. So you only get these effects when you do it in RMS. So when you don't do it in RMS, then just do the calculation. If you do the peak equivalent of this sinusoidal, like I showed you with the waveform comparison, then the peak voltage would only be at 3 U0, or actually it was lower if you look at the IEEE numbers. And that means on RMS, you almost go down to only 2 U0 or something like that. And there you see the growth rate is much lower. So you do not achieve the same thing, even though you think you're doing the testing. So it's very important that VLF testing is understood in RMS values. And then very critical, if you do it at AC, with a power frequency method, and you go fairly high in the test voltage, you go into the exponential growth rate. Here you see in the green graph, and then you're actually damaging the cable pretty severely, even if you just do it a few minutes. And then the common observation of our customers in the field is that they do this type of testing, and after that, their cables fail at a very increased rate. And now I told you about the study. So there was the study in Dortmund where they tested quite a bit of system of network and validated this 97%. And there was another big international study at TNB distribution in Malaysia, and they tested like crazy. They did like 17,000, more than 17,000 VLF tests. And funny enough, very different country, very different network, very different infrastructure, underground infrastructure, same numbers as in Dortmund, or let's say very similar numbers. So and these tests were done with the Senelec test values. So what we know is you get a 98% reliability, 97% reliability if you test at 0.1 hertz, if you keep it on for a sufficient amount of time, and if you test with 3 times U0. And actually, the guy that was overseeing this, Mr. Mo, he also published a few other papers, and he pretty much also noticed an observation: when you do testing at reduced frequency, those cables failed more often later on when put back into service. So you're compromising your reliability when you do the testing at reduced frequencies. Now that was VLF testing. Now you saw it, we're mid-90s, late 90s. We still have 20 years to go, right? So the main technology that is really the hot topic at the moment in the industry is the partial discharge testing. And why is that? Well, first of all, as an introduction, what are partial discharges? And I like this example. I stole it from a colleague of mine who used it first. What you see here is the C60 fullerene molecule, okay? It's a very complicated chemical structure. And if you want to describe this in geometrical shapes, you come up with crazy stuff that nobody understands without a math degree, okay? But you can also say, hey, listen, this looks like a soccer ball, okay? So there's a complicated way of describing things, and then there's an easy way. And for this webinar, we will stick with the easy way. And the easy way is partial discharges are simply a release of energy that nobody wants, nobody accounted for, and at a spot where the designer definitely did not intend it to be released. It causes deterioration because it's a gas discharge. Therefore, it reduces the life of the asset. It initiates breakdowns in the insulation until the asset completely fails. And then you have a cable fault. And thank God it's measurable. Otherwise, this would be a very academic topic if we couldn't measure it, right? So the key here is for field testing, it is measurable. And so you can pretty much summarize that, partial discharge is the predator of insulation. And the predator, this guy, right? You remember this guy. So PD is doing what this guy was doing in that movie. Now, why is the partial discharge test so effective and why is everybody so hyped about it? Well, because of this. If you look at the total numbers of cable faults and you allocate them to where it happened, the mechanisms and the parts of the cable, then an overwhelming majority is, related to workmanship issues, can be tracked back to workmanship issues. Some is cable pulling. By the way, in the presentation like a few years ago, there was a color coding mistake. So the green was where the yellow is and vice versa. So I've corrected this. I noticed this recently. So transportation damages are minimal, but they happened, Classic example, the guy, staples the bill of lading on the cable. Freak stuff is happening in the field. Cable pulling is really one of the mechanical issues, and then pretty much everything where humans put their hands on, right? This is the source for mistakes. So which would mean the accessories, terminations, and joints. And now, how do you actually measure this? So you have this technology that is pretty much measurable, or this effect that is measurable can be used with a certain technology and addresses these workmanship issues. There is a standard governing that. International standard IEC 6270 describes conventional and non-conventional PD testing. And it's very simple. Everything that is non-conventional is not conventional. Sounds weird, but the conventional test circuit is defined as exactly this and nothing else. Coupling capacitor, measurement impedance, something like this, calibration of the test circuit with an IEC 6270 approved calibrator, or that a device that calibrates as per IEC 6270, which is related to bandwidth and everything. And the unit of measurement is picocoulomb. Now, this picocoulomb also is defined, okay? The standard gives a definition of what is 1 picocoulomb, and you can only call your measurement results picocoulomb when you follow this circuit and nothing else. So anybody out there who is not measuring in accordance with 6270 does not really measure the same picocoulomb. Okay, it's like a guy showing you a banana and trying to convince you it's an apple, and no, this is a banana. What are you talking about? So you have to compare apples to apples, and this is done by the standard. And as I already said, this kind of silly distinction, if when this is conventional testing, then this means everything else is non-conventional testing, which is everything else. Acoustics with an antenna, inductive if you put high frequency CTs on it, corona cameras, all of this stuff is non-conventional PD testing. And then the conventional testing is based on the so-called traveling wave approach, which is pretty much very similar to a TDR. It's in the time domain. The traces look very similar to a TDR, but pitfall, they are not identical to a typical TDR trace when you hook up a radar and then you take a measurement in the cable. You have to think about this. It's a TDR trace if the TDR would be connected at the point where the partial discharge is happening. This is why the overall trace is to be interpreted a little bit different than a fault locating TDR trace. But essentially the physics is the same. You have the propagation of waves on cables, on low pass second order cables. And that means 50% of the pulse goes towards the detector, 50% goes to the far end, and then back to the detector. And based on this and the effect of dispersion and attenuation, you can calculate the location of the partial discharge. And now always a question, how far can you measure? That is like one of the first things customers ask. Well, it depends. A proper technical answer is it depends. So what does it depend on? Well, cable type. PIL cables have higher attenuation than XLPE cables. If you have any water in the cable, that has an effect, because that has an effect also on the velocity of propagation. The amount of splices, every splice causes a reflection, which is an energy loss. The neutral can have an effect. I put down there for the wind farms, very important. A lot of wind farms tend to use reduced neutral cables. So if you want to know if in such condition the TDR or the partial discharge trace looks good, or you can even measure partial discharges, the best thing is just to do a calibration in the field. Then you know the answer, right? And all of this has an influence. Typically, you can say, very typically, 3 miles. We had cables where you couldn't get 3 miles, very high attenuation situations, but we also had quite a few practical examples, field measurements, service measurements, where we saw much further than 3 miles. So this is just take this number with a grain of salt. Don't take it, and run away and tell everybody the Megger guy said 3 miles, and then you cry when your cable is just 2 miles. It depends on various things. And some cables, you cannot look that far into the cable. And in some other cases, we had cases of 10 kilometers, 6 miles, 15 kilometers, 9 miles, and that happens. So keep that in mind. In terms of what are we measuring during the PD test? Well, there is two very important things: the inception voltage, where the PD starts, and the extinction voltage, when it started, where does it stop? In terms of how to do the test, it's a stepped test. It is done at various different voltages that are increased as discrete steps. And first of all, you calibrate as per IEC 6270. Then you measure your de-energized circuit for the background noise that you pick up with the test device. And then you start with a sequence. This is just a suggestion, but it's a very good suggestion. But if you want to deviate or introduce more steps, you can do this. You need at least one measurement below U0, below operating voltage. You need the measurement at U0, and you should do 1.7 on serviced age cables and 2.0 times operating voltage on new cables. That is kind of the minimum, because you need to learn about the situation below operating voltage, at operating voltage, and above operating voltage. The inception voltage is much more important than the extinction voltage, because if you don't have inception, you don't have extinction. If you have inception, then the extinction is only interesting if the inception happens above operating voltage, because if it happens below, then you know, it doesn't matter. If you have inception below operating voltage, you always have PD during operation on that cable, and nobody cares about the extinction value, because it has no information, no value, because who cares where it goes extinct? You know, the PDs are burning at all the time, pretty much at any time when the cable is in operation. So the extinction voltage is important when you have inception at 1.3 or 1.5 or 1.7 U0. Then in terms of, so what can happen? These workmanship issues, freak stuff can happen in the field, like the craziest things. We sometimes get pictures sent by customers. So on the top there you can see they sanded too much, so you will have a void. Then on the right, the peeling tool slipped off. Then in the center and the picture in the middle, they also used an incorrect peeling tool. Then on the left, down on the left, you see contamination, and then on the right you see that the cutting tool, he slipped off and pretty much cut into the main insulation. So all of these things and many more, bug infestation, we've seen many things, and all of this will be visible during a PD test. Now, in terms of waveforms, the standard waveform for doing PD testing in the field is damped AC. Pretty much early on, since the 2000s, it was the first waveform that was proven also by a SIGRE working group and by SIGRE publications supporting the IEC standard, that this waveform is actually comparable to power frequency. And remember when I mentioned the resonance test sets? Well, in the mid-90s, when these resonance test sets came up, there was something that is called IEC power frequency range. It was something that they came up with in the standard to govern the resonance test sets, which would tune themselves to the cable capacitance. And sometimes the frequency is lower when the cable is longer, and then the frequency goes up when the cable is shorter. So they established this band, initially 30 to 300 hertz, 30 to 500, then it's 20 to 500 at the moment. And the next step will be 10 hertz, because for the very long cables, they have to go down to 10 hertz. So multiple series and paralleled resonance test sets can only charge these cables at 10 hertz. So that is the latest development there. And as you can see, it's over in 200 milliseconds. You have an oscillating dampened wave shape. You're charging the cable, you're causing the resonance, you have a power frequency related effect there. So it's a very straightforward waveform. And this is pretty much the waveform in terms of international testing practice. Then you have something that was solely used in the VLF world. Remember the cosine rectangular. And then I have to be honest, it was actually customers coming to us saying, hey, you have this waveform, can you use it for PD testing? And we said, well, we don't know. We've never tried that. It should work because it has the polarity reversal at power frequency, at the same slope as 50 and 60 hertz. But we have to test it. So there was a lot of field trials, studies, investigations done, and pretty much 2008, 2010, it was proven to be equivalent to damped AC and such equivalent to power frequency. So you will get power frequency, similar to power frequency results when you use this waveform as well. And here I just plotted the waveforms to compare them, and I also included the sinusoidal. Remember, that was the second VLF waveform that was invented. And technically, from a diagnostics point of view, it's very straightforward. Just use damped AC for diagnostics testing and use slope if you want to do a monitored withstand. Now, the confusion and this whole mess that a lot of people have in their heads, because it's so many different terms and waveforms and technologies, is pretty much, it was spawned from the market, because the market asked, hey, we already have the VLF test sets, can we use them for PD testing? As I just told you, customers came to us asking about cosine rectangular for PD. And the same thing happened with the sinusoidal test sets. Now, if you compare them and you zoom into the time base, you get this picture. You see that the cosine rectangular, the damped AC, and the regular power frequency AC are very similar in slope, and the sinusoidal is not. It's almost flat, okay? So the rate of change of voltage is very different. And that circles back to what I told you. Remember, local defects, two types. One that ignites because it's a void or a bubble or something, just by field intensity, which means reach the threshold, the ignition voltage, and it will ignite, no problem there. But then I told you the faults that are very sensitive to the rate of change of voltage, to the gradient in the accessories, in the layered interfaces. And you can see now why all practical testing pretty much shows that sinusoidal is not up to the challenge. If you want to do proper PD testing and get power frequency comparable results, you need to use a voltage that actually has been proven to be comparable to power frequency. So sinusoidal is not recommended for these things. And now I want to give you, to conclude with the PD section, just an example of asset management. And now I emphasize this, take this with a grain of salt. This is not really the full picture, okay? It's not the full story that I'm telling you here. So I got this information from a German utility company, and it's very common. So what they have is they have a matrix, a decision-making matrix, an asset management matrix. And what they do is they pretty much say, we have to categorize the cables for the testing, right? And this is a company that is doing 1,500, 1,600 tests a year, okay? So they say any cable that shows partial discharge is considered to be damaged. That's their terminology, okay? And any cable that shows PD at operating voltage is moved up to a state that is considered severely damaged. And then they do additional measurements for their decision matrix. So this is in terms of, from the test parameters, what goes into the decision-making process. So they say, is it an important cable, yes or no? Do I have more than 1,000 picocoulomb, yes or no? And the necessary condition to even get into the state was I have PD at operating voltage or below operating voltage, right? And then they say, okay, these four categories, we assign action times. And now, don't get this wrong. Action here doesn't necessarily mean cutting the cable and resplicing it or something like that. It just means take any action, which could mean, for instance, category 4, I come back in half a year and just retest it when it's fall or when it's summer, because maybe I did the test in winter and I just want to see what's going on. So this does not automatically mean repair or replacement. It could mean that, and in many cases it means that. But now, grain of salt, remember that this is not all of their parameters that goes into the decision making. And it's very important to understand that what they're trying to achieve here is to get a good base for decision making, not making decisions that are overly rushed. And to do that, they also incorporate joint technology and termination technology, previous trends and everything. So to get a full and very smart and intelligent risk assessment, you have to take into consideration everything that you have in terms of information. So there is certain joint technology known to be very resilient to partial discharge. There's other joint technologies that are known for fairly quick flashovers or failures once you have a certain degree of intensity in the cable. So you have to take these things also into account. You cannot just go by the numbers. This is just a guideline, and every company has a little bit of a different guideline. And you have to make sure not to do a one-dimensional decision making. So then as a summary, so for the last 20 years, damped AC is pretty much the technology. On average, the sinusoidal test sets are not recommended for PD testing because of these issues with the layered interfaces, with the joints and the end terminations due to the insufficient gradient, the dVdt or dudt. Damped AC is established. Slope is used for monitored withstand testing, and those technologies are comparable to a stiff 60 Hertz test set. And now the last part for the last 5 minutes is the 10 delta measurement. And now we talked about VLF as the withstand test and the partial discharge test to reveal the issues that the VLF test cannot find, because it was known from early on that at one point the VLF test is pretty much more of a safety test. You find gross defects, but there are defects, like I showed you, all of these, the mishaps in installation and the assembly faults, that will need 6 months, years, 5 years to produce a failure, and you cannot catch these in a 1-hour test. So VLF test is important because it's a voltage withstand test, but it has the function of a safety test when you talk commissioning testing. Now the 10 delta is the other one I told you. Now this circle there of the complete picture. And the 10 delta was the test technology for the global issues like the integral testing. So is it the diagnostic superhero that some people think it is? Well, unfortunately not. It cannot find many faults or quite a significant amount of faults. And why is that? Because it is a global method. And as an example, what you're trying to do or what you're doing during this test is you're after a certain, quantity. And this quantity can only be measured as a sum across the entire cable, because for the test set, the cable is one huge capacitor. So the weak spot might contribute more leakage, more losses, but this is kind of averaged out across the entire cable. So what you're trying to do is a local defect would be 1 drop of water. And now if you put that 1 drop of water into the glass there on the right, and the water in the glass has a certain temperature, and the drop of water had a different temperature, you're pretty much asking, tell me the temperature of this 1 drop of water. And you cannot do this. If you put the thermometer into the glass, it shows you the temperature of all of the water, the averaged, the global temperature. So this test cannot localize any issues. It's a global assessment, very important. So if you try to find the temperature of this 1 drop in the water, it won't happen. Now, when we say defects, what can it actually measure? Well, this is this effect of water treeing that initially was addressed by the VLF testing, because if you have water trees of a critical length spawning electrical trees, then you will able to find them in a withstand test. Now the 10 delta test can actually tell you the degree of damage done by water trees in the polymer insulation. That's what it's really good at in terms of diagnosing solid dielectric cables. And so What do you do during the test? It is a stepped test described in IEEE 400.2. And internationally, there's an additional step that is not being done in North America, which is 2 times operating voltage. So in North America, you stop at 1.5. You record a few values, a few loss factor, dissipation factor values in each step, and then you increase the test voltage. And then at one point, the test is over and you move on to the next phase. So in terms of experience, to do the setup takes approximately 10 minutes. Then you engage the test set with all the prep work and getting the mode right and everything. Takes another maybe 1 minute, and then you do these measurements in an automated sequence. Well, pretty much all VLF test sets today have this built in. And then you know that a 3-phase system takes approximately round about 40 minutes to be tested for 10 delta. And what you pretty much are after is the effect that if you have a water tree damaged cable, or if you have a wet cable in general, or a badly aged cable, this is very sensitive to voltage increase. So at one point, you can tell it's in a good condition if the 10 delta is pretty much flat, and it's in a bad condition if it's really showing exponentially increased losses by increased voltage. You're not measuring just the mean 10 delta, you also measure the so-called tip up, which is the delta 10 delta, and you base this on the value at 1.5 minus the value at 0.5 times operating voltage. You also measure the so-called standard deviation or stability. There's also evaluation criteria for that. So if you have very unstable results, this is also an indication of problems in the main insulation. And here's pretty much the standard that is, or the guide that is governing that. So in the IEEE 400.2, you can find these things. Now, what you're actually measuring there is pretty much the resistive losses versus the capacitive losses in the cable, right? And now the reality kicks in, and I told you that this initial picture I showed you of the 3 testing technologies is a little bit under fire. Well, more and more in terms of field work, the 10 delta is showing its limits, its limitations. So first of all, remember this term copolymer cables, which is these tree retardant cables. How is this tree retardant situation or this condition achieved? By introducing small amounts of other polymers and so-called additives, which are mainly acetone based. So they are much more polar than the actual cross-linked polyethylene. And because of that, you can pretty much say modern copolymer cable, you cannot really do anything with the 10 delta test in the field, because you're not really measuring the insulation, because these additives and the copolymer, the percentage, the low percentage of copolymer in there has such a masking effect that these numbers are really, really high. On top of that, copolymer cables, as shown also by recent research and a few publications, which I didn't have time to put into this presentation here, maybe next time, they pretty much verify that a copolymer cable shows a falling 10 delta over life. So any kind of life expectancy or even calculation of a number in years, this cable has so much years left, is impossible. The other thing is the influence of resistive and refractive field control in the layered interfaces, in the accessories. They have such an effect that also the 10 delta is kind of like ruined. The value is really high. Then you have the issue of mixed cables. You can pretty much say if you have any pilk in the circuit, it's already very difficult or impossible to tell anything about the XLPE or EPR part. So mixed cables the method becomes ineffective. And also these additives, they tend to have still chemical settling processes going on. So it's a part of these additives gas out over time, which causes the 10 delta to change. So if you do a 10 delta during commissioning testing, you might be misled to wrong decision making because you measure something that looks bad but actually is not. So what a lot of our customers are doing is either they don't care about 10 delta at all. I mean, it has its place, but a lot of people don't really care about it. They care more about the PD test. And another thing is they don't do the 10 delta testing until the cable is really serviced aged, something like at least a year under load, or we have customers that wait 2 years. We have customers that wait 5 years. The extreme example that I've encountered was 7 years. So they have work procedures because they got burned in the past. And so they pretty much wait for 7 years until they do any 10 delta testing. So the test has its merits, but also quite some limitations. Because of these limitations, the partial discharge test is the more preferred test. And that pretty much concludes the presentation. I have a few more slides, which I may show if there's certain questions, but I will give it back to Michael.
All right, thank you very much. So, as mentioned before, the presentation portion of our webinar has concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view recordings of previous webinars as well as register for our upcoming webinars on our website at us.megger.com/webinars. And be sure to register for our next webinar this upcoming Wednesday, October 28th, titled Electrical Installation Testing of High Voltage Gas Insulated Switchgear. All right, now let's jump into your questions. The first one I have is for Henning Ochen. Henning, in regards to slide 17, do all these standards apply to low voltage cables?
Well, if you look on, I think, slide number 17, the standards that are mentioned on that slide are all standards for medium voltage cables. So I assume what the person to ask the question means low voltage cable means 600 volt cable. So on all low voltage cables, to be precise, that have no shield, and typically low voltage cables have no shield, you cannot use any of these test methods, whether it's partial discharge or any dielectric test methods, because you cannot establish a defined electrical field. So unfortunately, for typical low voltage cables, you cannot do any condition assessment using any of these methods. And there are basically no other methods that can be applied for low voltage cables.
Thank you, Henning. Next question is going to be over to Marshall Bird. Marshall, which PD test is better, low frequency or DAC?
Well, this is a question that comes up frequently in the North American market. Each of these wave shapes they're equivalent, basically. The question really comes down to how convenient or easy is it to do a power frequency partial discharge versus a DAC. And when Robert was talking about the rate of change, that's what this comes into. And he showed the chart where basically the DAC and the power frequency and also the cosine rectangular methods are using a similar rate of change. and will get similar results. So it's not really which one is better. It's I would say they're equivalent, but there may be operational reasons why one might be preferred over another.
Thank you, Marshall. So, Robert, IEEE 400.2 mentions tip up to 1.5 through 0.5 U0 should we not apply table 400.2 when 3 U0 is used?
Okay, so you have to be precise here what you're talking about. The 0.5 U0 minus 0.5 U0 is related to the 10 delta. The 3 U0 is the factor for the withstand test. So the withstand test is the withstand test. It has its table in IEC, it has the prescribed values. That is just your hypot. The 10 delta is a defined test sequence independent of the withstand test. And it goes through these steps: 50% of operating voltage, 100% of operating voltage, 150% of operating voltage. And based on this process, you measure the stability, the mean 10 delta, and the tip up. And the tip up is what you described. So these are two different things. The one is the withstand test. The other one is the 10 delta diagnostics test.
If I may add to it, the withstand test is a go, no-go test. You want to see, does it hold or doesn't it hold? Where the 10 delta test is a diagnostic test, and you don't actually, on purpose, you don't want any diagnostic test. You don't want to drive to the limit where it could create a failure. You want to do a diagnostic test way below where the cable could fail. So that's why there are two, like Robert is saying, totally different tests for different reasons. And you're trying to also see different effects in the cable. One is for the aging effects, and the other one is for a pretty severe defect that would fail on hypot test.
Thank you. Next is over to Henning. What is the difference between commission and testing of service-aged cable?
Well, I think, Robert pointed that out in the beginning. He said, we have two groups of tests, either commissioning tests on brand new cables, or we have basically service-aged cables where we do condition assessment tests on. And what the difference is the new cable obviously has no aging. So there are no aging effects. So any defects we can measure on a new cable are due to basically either manufacturing defects or workmanship defects. Where the service-aged cables, we measure, in addition to those two types of defects, we also try to determine any effects from aging of the cable. So, and that's why you have different methods to address these different type of defects.
Just to add, I have a slide on this. I share it. So this is just a summary of various different interviews I had with customers, and I asked them, hey, what are you doing at the moment, and tell me about your testing practice. So this is kind of condensed. So for commissioning testing, which Henning perfectly described and explained, this is the testing on new cables, so newly installed cables. You have to do the voltage test, or you should do the voltage test, which is the withstand. So on new cables, you do as per whatever governing body you are adhering to, IEEE or IEC. So let's go with the IEC numbers here. So for instance, in Europe, they would do 3 times operating voltage, 60 minutes at 0.1 hertz. Now, this changes when you look at service-aged cables. And some of the feedback I got was, as you can read there, so if the cable, the service-aged cables, had already a certain number of failures, for instance, 2 or more, they would take down the testing voltage, the magnitude of the test voltage, but they would not compromise on the time, because remember, electrical trees need time to actually produce that flashover under VLF stress. So you should not compromise on the time, but you can take down the voltage if you had a few previous failures. And then there's something that you could describe as the Hail Mary test, okay? So if this test at reduced voltage completely fails, you know, you have an additional failure, what they do is simply they cut it down to a, you know, last resort test. They do 1.7 times operating voltage, and they see if the cable holds the voltage for, let's say, 5 minutes or something like that. And then they immediately start this procedure of taking action, because they know it's probably bad within 6 or 12 months. Okay, so this last last stand is a Hail Mary. They say, oh, it failed the reduced voltage test. The 1.7 is the ground fault value. You know, if you have a three-phase system, one phase fails, then the voltage is elevated to 1.7. So the cable insulation would see 1.7 times. And they just test for this. So in case of a ground fault, it's not going to fail immediately. So that's their strategy for serviced age cables. And after they pass the voltage test on new cables, they would do the diagnostics test with the damped AC. And the latest new trend is that you combine the two, the voltage test and the PD test, into a monitored withstand, but then you need a continuous waveform for that. So then it would be slope and not damped AC.
Thank you, Robert. Next question is over to Marshall. Marshall, how could we interpret results of tan delta? Is there a reference guide?
The short answer to this is yes, there is a reference guide. Robert talked about some of the limitations of tan delta, and he's popped up the slide. So, you know, you have a starting point, taking into account the limitations of tan delta testing that he talked about, mixed cables. It's been determined to probably not tan delta test on new installation. But one of the advantages of a tan delta test is you do have a starting point in terms of interpreting the results. So I would count that as one of the, from an operator point of view, an operation point of view, is you have a reference that you can go back to. And if you have a tan delta test that measures good, you know, that is what you're hoping for. If you have a tan delta measurement that measures bad, that's not within the standard, then you have some investigation to do, because, you know, that is a global assessment, and, you know, you would want to verify that you didn't fail the test because of a bad termination or splice. So you would have some assessment to do, but you do have a reference to start from.
Maybe I
Thank you,
can add
Marshall.
this reference that Marshall is talking about. It is contained in the IEEE 400.2 standard. There is a section about tan delta testing and limits and evaluation criteria. And many machines today, when you measure tan delta, have these built in, so they automatically compare the test results directly against the table from IEEE and give you a answer, you know, what's required to do with that cable. Okay. I'm not sure, maybe Robert can comment on this. I'm not aware of any tan delta table in any of the European standards, whether there is one. There didn't used to be one. Maybe there is one now, I don't know. But maybe Robert can comment on that.
No, there's just, you know, common test practices which are partially, sketched in the IEEE 400 guide. This is, you know, they have tables for, you know, quote unquote rest of the world, which, you know, if you take a look at them, you will see differences. But in the IEC world, there's no tan delta guide comparable to the IEEE guide in terms of, evaluation criteria and whatnot. And remember, the test practice is also different. They go up to 2 times operating voltage even.
Yeah. Well, I just want to say the IEEE is a true standard. It's not a guideline. The IEEE for 10 delta, as well as for hypo testing or withstand testing, is a true standard. Compared to, just to point that out, that difference, when you go to partial discharge testing in the field, the 400.3 from IEEE is a guideline. Okay, that's a big difference, because guideline gives you guidance, and the standard means you must adhere to it.
All right. Moving on to our next question is to Henning. Henning, does it make sense to do global assessments on brand new circuits before putting them into circuits?
Well, like Robert was saying, 10 delta is a typical method to do global assessment in terms of aging condition of the cable. So I answered that a little bit before when we talked about commissioning versus service age cables. Since you have no aging in new cable circuits, it really doesn't give you any information by running a 10 delta test. Actually, it could be misleading you to some extent, because of an effect on any new cables. When you make a cable, and most cables today are triple extruded cables, they use certain chemicals to help the extrusion process. And these chemicals basically are initially in the cable insulation. And so when you measure 10 delta, you measure the dielectric properties of the polyethylene, but you also measure the dielectric properties of these auxiliary components, which means the 10 delta is typically higher than what you would expect for pure polyethylene. So that's why it really doesn't make much sense to run, even not to get this famous footprint, because the footprint may be higher than what you expect to see. So it makes no sense to really run a 10 delta test on a brand new circuit. You should at least wait maybe 1 or 2 years for the cable to have operated under full load to, in a way, burn these byproducts off. And then you get a true reading of the 10 delta.
All right, thank you. Next is over to Robert. Are there any published criteria available to evaluate remaining service life of aged EPR cables using 10 delta testing?
The short answer is no. If you think about something like, okay, I collect certain amount of data, I put it into a model, and it tells you, okay, this cable fails in 2.8 years. That's a clear no. And the reason for that is the behavior of the copolymer cable. As I explained, that you have a falling 10 delta. So you cannot, it's funny, it's getting better, with age, right? And that would be the impression you get from that. You have the influence of the accessories. You have the technology of the joints. You have the cold shrink, heat shrink, slip on. All of these things have an effect influencing the 10 delta. You have even external influences. The test is very sensitive. So even to get the values is already pretty challenging in the field. And then taking these values and trying to calculate a remaining life is not possible. And I know it would be really nice, but there's no such thing on that. So you can what Marshall pretty much described and what Henning described, that's the best you can do. You take, for example, the IEEE 400, and you just do the testing, and you try to come up with a risk assessment matrix for your cable population, and then make a decision. Okay, this cable now went from further study advice to action required, and then you have to determine your own action.
I might add, in terms of, in IEEE 400.2, there is a section in there about copolymer cables, or what they call filled cables, which are in essence, many times they are also referred to as EPR cables. And there is a section about 10 delta measurement in there, and you will see opposite to the list for XLP cables and 10 delta values, which is really a standard for the EPR cables. These are just some typical numbers that people can use as a reference, but it doesn't have a standards character. It's just to give you some idea. I think there's also a list in there for some of the paper cables. But these are just meant as guidance and reference material. But there is something in that IEEE 400.2 standard.
All right. Next question's over to Marshall. Marshall, if we have a good reading about the tan delta test, does that mean that there's no need to perform a PD test?
This question has quite a few implications to it, if I understand it right. But we're really talking about two different tests that you're looking at the cable and trying to determine different things. The tan delta test is basically telling you what's the remaining dielectric strength of the insulation. So it's a global test. Whereas the PD, we're looking for a specific defect that is, or we're looking for a defect at a specific location. You could have situation, if you were doing a 10 delta test and you got a good reading, that doesn't mean that you don't have a weak spot. So if you have a concern, you very potentially would do partial discharge. You would do them both. It would depend on the situation. I'm not explaining this very well, but at the end of the day, depending on what you're trying to determine about that cable, would dictate what type of test you might want to do, not necessarily the result from one test or the other. They're giving you information about different failure mechanisms on the cable.
I might add, it's exactly what Marshall is saying. Depends what you're trying to accomplish. In North America, you can say there are two big groups why or reasons you do testing. One is for cable replacement, to identify cables that need to be replaced. And the other one is you have to do testing to ascertain or assess reliability of a cable. So, and that explains very well the difference between these two tests. If I only look for the decision which cables to replace first, I'm really looking at the age deterioration of the cable, not necessarily at a specific localized defect, which could be a bad splice. A bad splice I can fix and the cable is fine again. But if I have a cable that has been aged, thoroughly aged, and is on the brink of failing, that cable, I have no recourse to do anything. So from a cable replacement, that cable I need to replace, and the only information I need for that is I need the aging information. That means people who do typically cable replacement program, they prefer to do 10 delta test to help make that decision. Where on the other side, if people have very important cables like, special circuits to hospitals and so on, where they have to guarantee a service level, they have to do both tests because they need to know, is my cable, say, in jeopardy because of the aging condition, or is my cable in jeopardy because of maybe some bad component or a localized defect that can fail the cable. So that maybe answers your question, okay? So it all depends what it is that you're trying to do. That determines which methods you run. And I want to mention maybe one other test that we didn't talk about here, but with also, if you really want to do a complete assessment of a cable, you should also probably perform a sheath test. Because if the sheath is jeopardized or compromised, that means it's just a question of time till the insulation gets compromised. It's not very typical in the North American market, but other markets do, when they do a condition assessment of a cable, even on medium voltage cable, they will also do a sheath test.
All right, on to our next question to Henning. Henning, during VLF high pot test, does the difference of leakage current between three phases have any bad indication?
Now, that question is a little bit loaded because it says leakage current between three phases. If I have a cable, and basically all modern medium voltage cables, every phase of a three-phase cable, even if it's a three-core cable, has its own neutral. So the leakage current of one phase does not really have anything to do with the leakage current of the other phases, okay? So, but you can have certainly different leakage current amongst three phases. That is not something out of the ordinary. Even when it's the same as when you do 10 delta testing, you can have one phase that tests very well and two phases maybe that test not so good. So that depends really on the individual phase, so to speak, because it could be that either one of the phases has maybe a latent manufacturing defect that eventually will cause these issues, or it might be it was damaged at one, even on a three-core cable. Sometimes it get damaged on one side and that hits the one phase, and so it certainly can find out those differences when you do the leakage current test per phase and you do the 10 delta per phase. Then you will see the differences.
Also, just to add, okay, in terms of talking about leakage current, there's a difference between the waveforms. You can really just measure leakage current with the cosine rectangular. For a sinusoidal test set, leakage current is not defined. You can only get a charging current, which is not the same.
That's a very good point, because many times people are not necessarily aware of it, because even the sinusoidal test sets have, some of them have a let's say milli or microamp meter, right? And it's sometimes associated, then that means it's a leakage current. It's not the leakage current, it's purely the charging current you measure over those. And on a continuous AC sinusoidal wave, you cannot measure leakage current like Bob is saying. You can only measure the sum of leakage and charging and polarization and everything, right? But if you remember the chart that Robert showed you, when he showed you the depiction of the wave shape, on the cosine rectangular, you have the 60 or 50 hertz transition, and then you have a 5-second plateau phase. And that's how the leakage current can be measured, or why the leakage current can be measured on the cosine rectangular. At the end of the 5-second plateau phase, we can measure the leakage current. That's a very fundamental difference between the two wave shapes.
All right, next question's over to Robert. Robert, which Pico Coulomb values are recommended as good or bad, and at what voltage levels? Which is the instrument for measurement?
Okay, I intentionally avoided showing tables with recommendations, because you have to, it's kind of a loaded, as Henning just said, a loaded question, because if you show these values, you have to make sure it's clear to everybody that, first of all, it's just recommendations. There is no standard on these values. What we have found and what we typically also show and discuss in our seminars is that different companies have come up with certain thresholds for certain types of cables where they say, okay, here I start to monitor the cable more often, or here I take immediate action. So if you want a number from me, oh, it's 500 picocoulomb or 1,000 or 1,500 or 10,000, I will not give you that answer. But there's, common values, and they all emerge around they come together around the similar values. They are slightly different from company to company, but they're not so different when we're talking XLPE cables. In general, you can say that the PD testing, anything that is relevant, that is really a defect, will show up in hundreds and thousands of picocoulomb on your detector, on your test system. And but at the end of the day, you have to come up with your own risk management matrix and decision-making matrix. I showed you this one example from one German utility. They pretty much said, we sort the cable by importance. Less important cables will take, actions on and trying to monitor and fix the issue less often than more important cables, feeder cables. And then we determine a threshold where we're saying, okay, we know our jointing technology, splicing technology, remember there's cold shrink, heat shrink, slip on and whatnot. So we know by experience that we have this and this and this in the circuits. So we have to pay attention to that and that and that. And this is why assessment just based on measurement numbers, on values, is one-dimensional. It's not good enough. You need to take into account all these other things, maybe even circuit history. If a circuit is notoriously known for failing, then you probably take a different approach to this circuit for some reason than another circuit that might be electrically identical. Another very interesting thing is the company, which I took as an example, they also have the work practice to cut out all three phases, no matter what, when they have a fault. So let's say A phase fails, they will cut B phase and C phase as well to keep the cables the same. Okay, and then they check, okay, maybe is there a common denominator, who built the joints and whatnot. So they do all this additional assessment far beyond just the numbers. The numbers are just a starting point. But what I can tell you, for instance, the strictest utility company in the world regarding these values used to be Singapore, and they had a very rigorous policy of cutting everything out at 500 picocoulomb. But from our field expert, who's doing a lot of testing and training with the customers on these issues, he told me recently that even they eased up on the criteria because they learned that it's not necessary for them in their network to take such a rushed action and such an early action. So I believe they moved up to 1,000 picocoulomb. But the intention is always the same. I have to repeat this. You have to go beyond the numbers. The numbers are a starting point. They give you indication, inception voltage, extinction voltage, and then the activity that you measure. But you have to take into account more factors for a proper decision making.
Maybe just to add a little bit to it, it's, you have to distinguish when you compare numbers between what type of a cable you have. You have a solid dielectric cable, or you have a paper oil insulated cable. Or you have solid dielectric accessories, basically, that are resin type accessories, or heat shrink, cold shrink, or whatever. and you have liquid-filled accessories, right? The liquid-filled can typically take much more PD because they're oil-filled for the most part. They can take much more because the oil is snuffing out the PD compared to the solid dielectric. Anything that's solid dielectric that has PD has a void. The void doesn't get any better. There's nothing to snuff out that PD. So you can see, you know, a paper cable, any paper cable that you test in the field, even a new one, a good one, has maybe a few hundred picocoulomb PD, and that's fine. It will live with us forever. But on the other side, the solid dielectric cable, if it has probably more than 20 PC, if you can measure it, then also probably would fail already. So it's the numbers. You need to know exactly what you're comparing these numbers on, and it sometimes goes even so far that you can even on a splice. You need not just to say a splice, you need to know who makes that splice, because the materials are different from different manufacturers, and they have different, let's say, resistance to partial discharge. And so it becomes very, very tricky. Now, if you operate in your own system and you have enough data, then you can come up with some, I think, references and guidelines, but you need a lot of data.
If I could just make a comment on this topic too. One of the things that's easy to do with partial discharge values, when you're doing testing on a set of new construction where all your splices are terminations, they should all have the same relative value. And so when you're doing the PD testing, if you have an outlier, you know, I have so many terminations, they were all built at the same time, they're all in the, you know, they're all in the same construction project, I would expect to see the same value within reason across all of them. So if I have an outlier, I may not know why, and I may not know what the value should be, but I know it's significantly higher than its brothers and sisters. And so that, you know, that from an interpretation point of view is quite easy to do. Yeah.
Well, even more so on a brand new circuit, you know, I mean, there are companies that have the method to say, okay, on a brand new circuit, everything is done properly. I shouldn't see any PD, period. Okay. So that's the, because it is correct. If everything is, if your splice and terminations are properly done, you will not see PD in that circuit. So it becomes much more a problem on service age cables to interpret these levels, because you will have levels, and then it becomes a question how to interpret them.
All right, I think we have time for one last question, and I'm going to direct back over to Robert. Robert, what do you really obtain doing a commissioning test through monitored withstand testing, including 10 delta?
Well, as I tried to explain, I mean, I could give you a very short answer, not much or nothing, right? The 10 delta is really not an effective, useful test on newly installed cables, to put it plain and simple. The reason is you measure something, you know, we explained to you like the stuff with the copolymer cable, the additives, the cable has not yet seen load, the falling 10 delta over the lifetime of the copolymer cable, the influence of the accessories and whatnot. Then even external conditions, humidity, maybe dirt on the end terminations, so you have additional creepage, so then it becomes a guarding problem maybe, or a cleaning problem, all of these things. And the preferred monitored withstand test, and which is this, you know, hot topic, latest hot topic, is you do the VLF to have your safety test. If you switch on, it's not going to explode or fail. And you monitor the PD activity, because just let me share you one more slide in terms of for this last question. If we're talking acceptance test, commissioning test, this slide, you have to remember the cable as it is comes out of the factory, hopefully fully checked for quality, right? Because they should do a PD test in the factory for the reels. So you may have some transportation damage, and you may have some odd things going on in storage, hopefully not. And then you pull the cable into the trench, and the cable, you can assume the cable comes out of the factory in good condition. What you do then is you put your hands on the cable. And this is why these workmanship issues are such a problem, because the cable itself is supposedly good, and now the human factor comes in, and if somebody is doing a bad splice, this will show up in and during the partial discharge test. And in most of the cases, most of the scenarios, not on a 10 delta test. The only thing you might be able, to see with a 10 delta test that is remotely, related to a localization, thing would be a wet splice, especially when you listen to Marshall's answer. If you have 3 phases and maybe just one of the 3 phases is soaked with water, or one joint, the 10 delta might be different there, but then you still have to find out where it is. So it's, again, not a localization test, but it might indicate a very specific problem with water in the cable. Now, on a new cable, unless you left it open overnight, it rained and whatnot, there is no aging condition in there, and nothing you can measure in relation to water. So, plus, again, the effect of copolymer cable additives and whatnot. So you're not measuring anything useful there. So for a monitored withstand test, you should pay attention to your layered interfaces, terminations, and splices, because this is really the source of most of the failures in the cable. So it's much more valuable to do it with PD instead of 10 delta. Okay, so I don't see much value to do this test with 10 delta on new cable.
All right. Well, it looks like that's all the time we have for questions. We apologize if we did not get to your question today, but we will be working to follow up with you offline. As a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all again for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. Once more, I'd like to thank you all for attending, and I hope you all have a great weekend.